Before the 1990s, the idea of planets orbiting stars beyond our solar system was merely a theory. But then came one discovery after another, and the field of exoplanet study has boomed over the past 2 decades. This episode, I got to speak to astronomer and exoplanet hunter Beth Biller at the University of Edinburgh to get her thoughts on a groundbreaking new instrument that will allow her to capture direct images of young exoplanets in orbit around their host star.
Hi, I'm Beth Biller. I'm a professor at the University of Edinburgh, and I study exoplanets. In particular, I work on direct imaging of exoplanets, so actually taking pictures of planets orbiting stars other than our sun.
That's so cool. It's always really interesting to talk about exoplanets because you sort of forget that, it's only really been about, was it like 25 years since the first
25 years.
Yeah, since the first ones were discovered. I mean, what's it like being part of this field?
It's a really exciting field to be part of because it is one of the fastest growing fields in astronomy, if not the fastest. Because, 35 years ago, people were honestly saying, oh, will we ever find planets around other stars? Are there planets around other stars? Which, now sounds pretty ridiculous to us. We find them almost everywhere we have the sensitivity to detect them.
Yeah, I heard it was a year or two ago. I heard that if you're looking up at the night sky, pretty much every single star has a planet around it, sort of on average.
On average, yes. Yeah, they're that frequent.
Was it something that you were thinking about when you first decided that you wanted to be an astronomer?
Absolutely. So I was interested in astronomy as a little kid, and I kind of drifted away as a teenager. But when I was in high school was actually when the first exoplanets orbiting sun-like stars were detected. And that made a huge impression on me. And that was kind of the moment where I thought, okay, this is what I want to do. Cool. And now you sort of find yourself working with these new instruments, which is what we're going to be talking about today. So it's the ERIS and the NIX instruments. So I was wondering if you could give us a bit of background about them and what they do and what makes them so special. All right. So ERIS and NIX are new instruments for the Very Large Telescope in Chile. And yes, astronomers are not great at creative names for telescopes. But what ERIS is, it's a multi-purpose instrument that uses adaptive optics. So adaptive optics is a technique essentially for correcting the distortion and turbulence from our atmosphere, which is fundamentally limiting our ability to image things at high resolutions. ERIS is a replacement for NACO, a previous adaptive optics imager, but ERIS really builds upon and improves on what NACO could do. So ERIS-NIX in particular will be able to image at somewhat longer wavelengths than NACO, or rather image well. So NACO was able to work up to maybe about 5 microns, so up into the mid-infrared. But those are wavelengths we really, really struggle with the atmosphere at those wavelengths. ERIS has a number of improvements that lets it get much higher quality data at those wavelengths in particular.
Why do you need to observe at these different wavelengths?
Well, one reason for exoplanets, especially the sort of exoplanets I study, that's where we see the peak of their emission. That's where they are brightest. The planets I study, the directly imaged planets we know today, are rather massive planets. So they're kind of what I would like to refer to as baby Jupiters. They're like Jupiter, but they've just formed, and they're quite hot from the energy of their formation, which means they're still kind of glowing. They're about the temperature of, say, a candle flame. And if you've ever looked at it, used an infrared camera, you'll notice that things that are warmer look a bit brighter. So they are brightest at wavelengths of about 1 to 5 microns, and especially 3 to 5 microns. And that's why we're really pushing to those wavelengths. It's the best wavelengths to try to image that particular set of planets, or at least that's why I am. There's all sorts of other science cases for ERIS as well, with other priorities.
In the sort of context of the universe, the heat of a candle flame doesn't really sound all that hot.
It isn't. It's just hot for a planet. Indeed. And this is actually a funny thing across different fields of astronomy, is that different fields have very different calibrations of what's hot and what's cool, right? So these planets are a bit cooler than what we would refer to as a cool star. A star that is cool is maybe a star that has an effective surface temperature of 2000 kelvins, right? So that to us sounds fairly hot. Whereas then when you start talking about, say, the interstellar medium, the space in between different star systems, which is mostly empty, but sometimes is full of, it has some gas clouds in it. Those gas clouds we'd call a cool one, maybe about 50 or 70 Kelvin. And a warm gas cloud in the interstellar medium would maybe be 150 or 200 Kelvin. So very different calibrations of temperature scale.
And so these planets, these exoplanets that you're going to be looking at with the instruments are very young. So does that mean that, like, are they sort of as developed as they will be, or will they be? Are they so young that they will continue to grow and change over time?
They will continue to evolve over time. One reason we're interested in these particularly young planets is because we're catching them right after the epoch formation. We can try to understand the mechanisms by which they formed. That's part of it, is to look at how planets form in particular. But they are definitely not in their final configuration. They will continue to cool over time. So in comparison, Jupiter is quite cold. And we expect if you take one of these baby Jupiters and wait a few billion years old, it will get to the temperature of Jupiter.
It must be quite difficult, though, to sort of see planets amongst the glare of a star, because presumably the star is just so much bigger and so much brighter than a planet, and you're looking at it from so far away. How do the instruments sort of make up for that?
Yeah, so the model I use to try to explain this is it's kind of like trying to image a firefly next to a lighthouse.
Right.
And except that you're not sitting on the beach looking at your firefly and lighthouse. If I was in Edinburgh, the model of the scale would be that firefly and lighthouse would be in Dublin.
Right.
So that's the sort of contrasts and resolutions you need. So yes, there's a lot of technology that goes into making that possible. And that is built into ERIS's design. So the first important bit of technology is that adaptive optics I was mentioning, to basically correct for the turbulence of our atmosphere. And once you correct for that turbulence, if you have a telescope of a given diameter, the resolution of that telescope gets better as 1 over the diameter. So as the diameter grows, you can resolve smaller and smaller objects if you are correcting for the turbulence of the atmosphere, or if you put your telescope in space.
Yeah.
That being said, that doesn't overcome this contrast issue, right? The planet being much, much, much fainter than the star. So ERIS has chronographs to do that. ERIS has a couple different designs of chronographs, and there's a lot of details in there that I'm not going to get into. But essentially, those chronographs are what allow you to overcome that enormous contrast difference and actually image that planet, that very faint planet next to your bright star. Little historical fact why they're called chronographs. The first one was designed essentially to block out the disk of the sun, so you could see the outer atmosphere, the corona of the sun.
Ah, okay, cool. Yeah, actually, I was reading about those, and I was also came across a bit of info that you personally were involved in the design of some of the filters that are going to be on the instruments. Is that correct?
Yeah. So with my group, I designed and provided a custom filter for ERIS. And that custom filter is in the infrared. It's nestled basically in between 2 other infrared filters in ERIS. And if we essentially take pictures of planets in those 3 filters that are covering a specific wavelength range, we can use the pattern of brightness, right, where they're bright and faint, to match against the spectra we expect to see for those planets and determine if a given candidate looks like a planet or not.
Mm-hmm. Yeah, I mean, I think a lot of our listeners will be amateur astronomers themselves, and they'll probably be quite familiar with the use of filters even on sort of small refractors and telescopes that you use in your back garden. Are the sort of filters that amateur astronomers would use, are they really that different from what you're using? Is there sort of
not at all? Yeah. It's exactly the same thing.
I'm also really interested in the adaptive optics aspect of it. So does that correct for the disturbance of the atmosphere in sort of real time, or is it sort of like a post-processing thing?
It needs to be nearly real time. So the way that works, we're working in the infrared. So we keep the infrared light for the detector. But then the telescope collects light over a broader wavelength range, so we can look at the optical light. And if you look at that very, very quickly, we have an idea of what a star should look like, right? In the perfect diffraction limited case. So we have a model of that perfect wavefront, and we can tell how far the wavefront of the incoming light is deflected from that due to turbulence in the atmosphere. So we can measure the aberration, essentially, the distortion from the atmosphere. And very quickly, you have to do this like kind of with millisecond sampling because it changes over time because the atmosphere is very turbulent. So you measure this, and then we have an additional piece of hardware, a deformable mirror. And the deformable mirror also has to be run very quickly. But essentially, you measure what the atmosphere is doing, use the deformable mirror to basically do the opposite of that, to correct out the atmosphere. And it's moving very quickly to do so, and essentially dial out the atmosphere.
Yeah, because I mean, that distorting effect of the atmosphere is obviously why, space telescopes are launched, to get beyond the atmosphere. So does this sort of adaptive optics, does that sort of, render the launch of space telescopes unnecessary? Can you sort of get around having to do that?
Yes and no. So, adaptive optics really help us getting the full potential of ground-based telescopes. We never perfectly correct out the atmosphere. And we also have a range of conditions. You can get very good nights where you do almost get the same performances you get from a space telescope. You have other nights where it's just kind of hopeless, and that's just how it goes. So it definitely helps. I also think you get a sensitivity boost from being in space too, because the light doesn't have to go through the atmosphere and get absorbed by the atmosphere. And depending on what wavelengths you're working at, there are some wavelengths we just can't do from the ground at all.
Okay. Yeah.
So there you do have to go to space.
Yeah. No, I'm also really interested in the fact that it's going to actually be taking photos of exoplanets. What will these photos look like? And, are they the sort of photos that would make sense to a non-astronomer like me? Or are they sort of,
Yes, they would make sense. Let me show you one.
Okay.
All right, so what you're looking at is about a decade's worth of imaging of 4 planets orbiting a star a bit more massive than our sun. This is the HR 8799 system. So these are all baby Jupiter planets. They're a bit more massive than Jupiter and much younger. Again, about the temperature of a candle flame or so. So we're looking at the infrared. And the reason you see them moving is this is over 10 years. This is just a set of images taken over many nights. And that's the actual orbital motion of the planets that you're seeing as they orbit their star.
That's absolutely incredible. So the blacked out bit in the center is obviously the chronograph doing its thing.
Yeah, that's what's been blocked out.
Obviously, people listening to this on the podcast won't be able to see the video, but I think I will share the link to the video that you are showing me at the moment in the podcast description. So if you just scroll down to the podcast description, if you're listening to this, and click on the link, you'll be able to see the video that Beth is talking about. But yeah, that looks absolutely incredible. I've never seen anything like that before. I didn't realize that they could actually get, such sort of crystal clear images of exoplanets like that. Yeah,
so there's about 20 or so exoplanets we have images like this right now. Again, these are very massive, very young exoplanets. The goal long term is to push down to lower mass and cooler planets also.
How does the instrument actually work? Does it sort of work like autonomously with sort of, artificial intelligence, or does an astronomer like yourself have to sort of specifically sit down and tell it what to look at?
The latter. Yeah, so there will be someone who has to run the instrument. So this has changed over the course of time that I've been in astronomy. It used to be fairly frequently, you went to the telescope, and as the observer, you sat and actually ran the camera itself. So like a bit more complicated than maybe the camera on your phone, but they're not that different.
Yeah.
So I've had many nights at the telescope where I sit there and run the camera, and there's a professional telescope operator who moves the telescope around and actually runs the telescope. That actually still happens, but most observatories have their own staff astronomers who will do the observations. So mostly they have software to set up exactly what you want in the observation that automates the steps. So you have essentially the script of what's going to happen and all the commands to go to the telescope and the instrument. And the observer who's there on the night will run that script.
Mm-hmm. So, and obviously, as we said, this is going to be in the Very Large Telescope in Chile. So can you sort of be sitting in your house in Edinburgh and you go online and you tell the telescope what to look at, and then you go to bed, and then in the morning you've got all the data and all the images?
Yes, but there's someone sitting at the telescope running the telescope and another person sitting at the camera running the camera in this case. It's not the telescope doing it all on its own. There are robotic telescopes who do that. But I don't think there's an 8 meter class ones that do at this point.
Okay. So how will you decide where to look for exoplanets? Are there any sort of specific, star systems or exoplanets that you're kind of can't wait to actually get an image of?
So there's two aspects of this. There's trying to detect new exoplanets and characterizing the ones that we know. So with Eris, I'll start with characterization, actually. What's exciting is to be able to characterize them a bit better at wavelengths from 3 to 5 microns, where most of the ground-based data hasn't been that great. Mm-hmm. So there's a few really key systems, like the one I showed you, the HR8799 system, that'll be very interesting to look at longer wavelengths. For detection, Eris has huge potential for that as well. And I have a PhD student who's actually working on a paper on this right now, trying to decide what the best set of stars to search for planets would be in this case. Now, as I mentioned, we mostly target younger stars, but these are, young. We were talking about like how temperature scales vary by subfield. Astronomers have a very different definition of young than the average person. Yeah. So, by young, I'm talking in this case, 30 or 40 million years old. Very young is only 1 or 2 million years old. So to find the young-ish stars, what we do is we look for stars that happen to be moving together in the sky. And the reason they're moving together is that they've formed relatively recently from the same cloud of gas and dust. And they're still kind of mostly moving in the same direction in the sky. Mm-hmm. And these are what we usually call, again, creatively, moving groups.
Yeah.
And most of the known directly imaged planets are around some of these moving group stars. The issue is that there's been a lot of surveys of these stars already. So we're trying to decide, is it worth focusing on these stars, on other young stars? For instance, younger star-forming regions that are maybe 1 or 2 million years old, but a bit further away. We're also looking into, for instance, so Gaia is another space mission. So Gaia has been up for about half a decade now, and is measuring the distances to essentially everything in the sky, and just measuring how those stars are moving around, just these very small little movements on the sky. So we can look for stars that have a little bit of an additional wobble than we would expect in the Gaia data that can be evidence for a companion, and attempt to follow those up with Eris. So we're trying to balance all of these approaches and decide what the best sample of stars for a survey would be, but I'm not entirely sure what the answer is yet.
Okay. Yeah, no, because I was sort of thinking about this and that whole thing about, being able, looking up at the night sky and there being on average a planet around every star. And there would almost be sort of like, well, for me anyway, there would be sort of the temptation to just pick the sort of the most famous stars that we know of in the night sky, like Sirius and Polaris and, Betelgeuse and all those stars that we look at every night. And just to see what's around them. Do you ever sort of get tempted by that sort of thing? Yeah,
and people do that. So the problem is most of those are old.
Yeah.
Which means that if you're working in the infrared and looking for the intrinsic light from the planet, those are cold planets. And so they're hard to image. That being said, especially for the very closest ones, it's definitely worth a very deep look, right? Especially for instance, Proxima Centauri, the nearest star to us, has 2 known exoplanets. One of which may be imageable with extremely large telescopes, 40-meter telescopes that will come online in the next decade. And very recently, I think this was just out this week, there is a paper looking actually at these sorts of wavelengths, like 3 to 10 micron wavelengths, looking for planets around Alpha Centauri A and B. Mm-hmm. And they actually do have a candidate. They are properly circumspect about this candidate because it's not confirmed. But for the nearest stars, if you go really deep, yes, there you have the potential of imaging some fairly cold planets.
That's absolutely incredible. That's so cool. What is left to do from your perspective? I mean, because the instruments will be on. Well, the instrument will be on its way to the VLT. Will you get a chance to go out to Chile, do you think, whenever travel restrictions are lifted? And what's sort of left to do before you start, getting down to using these instruments and observing?
So right now the instrument is being tested in Germany, and then we'll go to Chile. There'll be, I think, another round of testing and then commissioning in Chile to getting everything to work. I'm hoping that some of my students and maybe myself will go out for some of the commissioning and certainly maybe some early observations. It's looking like 2022 for that, for obvious reasons.
Yeah, indeed. I mean, it must have been tricky preparing all this under sort of COVID lockdown in terms of things like transporting to Germany and all the associated issues with that.
Yeah, I haven't been too involved with the lab work, but most of our site has been more or less closed down.
Yeah.
It's been the people who have been actually building instruments in the lab who have been going to the Royal Observatory site to continue that.
Yeah.
And certainly the building aspect of ERAS was finished during lockdown.
Okay. Yeah, it's incredible that these, and I've sort of seen across sort of space flight and astronomy, the people I've been speaking to over the past year or so, it's just found a way, astronomy, hasn't it? It's just, the stars keep moving and astronomers keep looking up at the night sky.
Yeah, I mean, certainly there was a period where most of the professional telescopes were closed.
Yeah.
Which is frustrating because you don't get that time back.
Yeah.
But given the geopolitical situation, that wasn't the only choice.
Yeah. Cool. Well, thanks very much for speaking to me today, Beth. I'm sure you're very excited to get observing, and I'm really looking forward to seeing what you and your colleagues come up with over the years to come.
Thanks for inviting me on. It's been really nice chatting.